আচ্ছা, in last class we have discussed the closed system. Okay, the slide is visible.
Yes, ma'am.
Yes, ma'am.
Okay. So what happened in closed system, that energy balance? So this is a closed system. Closed system means that within the within the system boundary, whatever the heat you are applying or the work you, that is the output, that exchange energy within the system boundary. So for this closed system, the governing equation is always accumulation is equal to input minus output. And what is accumulation? That is that energy, the final energy or the differences energy. In closed system, we can see three types of energy: internal energy, kinetic energy, and potential energy. So the differences, that means the net changes of the input is equals to net input of the system. So overall energy balance for a closed system, that is the differences or changes of internal energy, changes of kinetic energy, that means difference, or net changes of potential energy. This all summation is equals to Q minus W. Q is a heat and W is a work done. Okay. So that was for closed system. Now open system. Open system means that it exchanges the heat, the work done with the boundary, with the that sorry, not boundary, with the system, with the surrounding. The system exchanges the heat or the energy with the surrounding. So in closed system, we have seen the kinetic energy, potential energy changes, and the internal energy changes. But in case open system, we other than these changes, additional changes we can see, that is the pressure and volume. So pressure and volume, that is, if this is an open process, we have a mass flow rate or mass, then kinetic energy, potential energy, internal energy, and the pressure and volume. Okay. So for open system, the equation is, that means the governing equation is same: accumulation is equal to input minus output. But in case of input and output, we have to incorporate some terms, that is the changes of the pressure and volume. So WFI, that is equal to W out minus W in. This is the work. And W out, W in, work input and output changes. So W is equal to PV. And so pressure out, volume out minus pressure in, volume in. If you have IJ components, then we can write this way. Okay. So now the total rate of work, that is WFI, that done by a system on its surrounding, we can divide it into two parts, that is the WS and WFI. Now what is the work done? That is the W. And WFI, we know that is the changes between output and input. And what is WS? So WS, that is a shaft work. If you have a piston, then shaft is there. So the rate of work done by a fluid on a moving part within the system. Okay. That means you are the piston or the turbine in the system, there is a rotation, and you are changing several time, you are giving the pressure on the piston, and same pressure that is delivered to the fluid by the piston. So that is the shaft work. You are working on the piston, and this work is delivered to the fluid or some gases. So that is the shaft work. So W is the shaft work, and what is this FL or FF? That is a flow work. So rate of work done by the fluid at the system outlet minus the rate of work on the fluid at the system inlet. Okay. So you are giving the pressure, and what happens when this pressure is delivered to the fluid? The volume expansion may be there, or volume compression may be there, or sometimes phase changes is there. How? That means the fluid, that if it is a liquid, that may be converted into gas, or the gas converted into liquid, depends on your pressures. Okay. So that is a flow work. So summation of the work on the system, that on the system, the work, that is a summation of the shaft work and the flow work. Now the if you have a continuous system, continuous system means you can consider the piston turbine. Then that is a same formula: accumulation is equal to input rate minus output rate. And we know what is initial system energy. That is, in closed system we have seen the internal energy, kinetic energy, potential energy. In open system we are watching this P and V, product of PV. Okay. Same for the output. So energy transferred Q minus W. That is the accumulation part. Accumulation. So the final equation looks like this. After arrangement, we can see the equation, that is del U plus del KE plus del PE plus del PV is equal to Q minus WS. Okay. Q, that is the rate of heat energy in, and WS, that is the rate of work done by the system as a output. Now, now this del U plus del PV, that we can write as a del H. So del H is equal to del U plus del PV, and this del H is a enthalpy of a system. Okay, that is, del H means enthalpy changes, and H is equal to U plus PV. So what is enthalpy? If you later we will study what is enthalpy. So enthalpy is a summation of internal energy and the volume and pressure working on the system. That means you are applying pressure, and due to this pressure how much volume that is changing. This changes plus the internal energy is giving you the value of enthalpy of a system. This is a thermodynamic property, enthalpy. Now we have some thermodynamics law, because in energy balance we require them. So first, the laws of thermodynamics define physical quantities like equilibrium, temperature, energy, entropy. And, and what is zeroth law of thermodynamics? That if two systems are each in thermal equilibrium with the third system, they are in thermal equilibrium with each other. This law helps define the concept of temperature. Okay. Now, first law of thermodynamics, that we know several times we have studied. First law of thermodynamics, that is conservation of energy. Energy cannot be destroyed, or energy cannot be created. Okay. So the when the energy transfer as a work, as a heat, or with matter into or out of a system, the system internal energy as per the law of conservation energy, that is, the energy is constant. Second law of thermodynamics, that says that process that involve the transfer or conversion of heat of energy are irreversible. The second law, that is about the quantity of energy. It states that as energy is transferred or transformed, more and more of it is wasted. Okay. Now, third law of thermodynamics, the entropy of a system, entropy means randomness. Okay. So the entropy of a system approaches a constant value as the temperature approaches absolute zero. Okay. The entropy of a system at absolute zero is typically close to zero. That is a third law of thermodynamics. Do you have thermodynamics subject in second year? Hello?
Yes, ma'am. No, ma'am, we don't have in second year.
In fourth year, you have. Hello?
Yes, ma'am. Uh, we are from BSc. In BSc, we studied thermodynamics, but we don't know about the whole syllabus of BTech polymer. We
Okay,
get the third semester and fourth semester syllabus only.
okay, okay. Then I hope that some of you know the thermodynamic subject. Maybe. So you are quite familiar with these laws also.
Yes,
Now,
ma'am.
okay, now the entropy, this is a thermodynamic property, and this entropy, you can say this is a extensive property. Hmm. Now, what is entropy? That is formula. We can see that del Q is equal to TdS. This del Q, okay. So what is entropy? Entropy, that is a randomness of a system. This entropy actually measures that the system thermal energy per unit temperature. You are applying some temperature on the system. Now the system that gets some energy, and the molecules, they are excited that time. So that creates a disturbance or randomness. So this randomness, that measures by the entropy. Okay. So this entropy is a physical measure of lack of physical information about the microscopic detail of the motion and configuration of a system. So this is a formula that dq is equal to tds, and what is dq or del q? That is a product of the temperature T into ds. And what is ds? That is the system distance, or you can say the system and the sources of the destination of the heat with the increment. So temperature is parameter, you are applying temperature, and ds, that is the sources increment, destination of the heat. This is the parameter. So del q, that is a heat. So entropy gives us the value of our randomness of a system. Now another property, that is enthalpy. Okay, enthalpy, that is measurement of energy in a system, and this is equivalent to the total heat content of a system. Okay, that is a qualitatively measurement. Now if we want to know quantitatively, then we have a formula, that is H is equal to U plus PV. That means internal in a summation of internal energy and the product of pressure and volume gives us the value of enthalpy. Okay, this enthalpy, entropy, these thermodynamic property are related with the second law. Hmm. Now what is specific enthalpy? Specific enthalpy, that is if you divided all the terms by mass, it will gives us a value of specific enthalpy. H by m, then that means specific enthalpy. U by m, specific internal energy. PV by m, specific PV by m. PV is a pressure that does not depend on the mass. So V by m, that is specific volume. Okay. So when the specific term is coming, we need to apply this bar sign. Okay. So this is the enthalpy part. Sound com. Now we have one numerical that only just theory basis numerical. The specific internal energy of a gas at 25 degrees centigrade and 1 atm is 3.79 kilojoule per mole. Well, specific internal energy, that means the U bar, that value is 3.79. Temperature, that is written 25 degrees centigrade, and pressure is 1 atm. Okay. Now the specific molar volume under the same condition is 24.5. So V value is given, V bar. The rate at which enthalpy is transported by a stream with a molar flow rate of 200 kilomole per hour. Calculate the specific enthalpy of the gas. So enthalpy, specific enthalpy, that is a H bar is equal to U plus PV. We have the value of U, then P is value is given 1, V value is also given. So from that we can calculate the H bar, and we have 6272.46 joule per mole, this value. But we need to calculate the specific enthalpy rate, that means the enthalpy transport rate. So here the rate of, that means mass flow, molar flow rate is given, that is 200 kilomole power, and we have joule per mole. So we need to convert this kilomole into mole. Therefore H is equal to N, that is the mass flow rate of the system, into the enthalpy, specific enthalpy. This gives us the value of this enthalpy transport rate. Very simple numerical. Now, for this energy balance, some definition we have to know and some parameter we need to know. So first parameter, important parameter, that is a sensible heat. What do you mean by sensible heat? That means that is the temperature of the system. So in absence, that must be the temperature of the system in absence of phase change. So the sensible heat change, that is determined by using a property, that is a specific heat capacity at a constant pressure and constant volume. And we have two formulas, that specific heat capacity, that is Cp, that is a summation of Cv plus R. So R we know, that is a universal gas constant, and Cv, that is the constant volume. So this formula we can apply only for the ideal gas system. Now if we have liquid and solid, then the specific heat, that quite equal with the constant volume. Okay. That means for ideal gases, this Cp value, that changes with the volume, and the uh, that depends on the universal gas constant. Now one rule is there, that is a Kopp's rule, that actually helps to determine the Cp value. So Kopp's rule is used to roughly estimate Cp values for material based on their atomic composition. So that is a Kopp's rule. Now another parameter, that is a heat capacity, or a specific heat capacity. we have the formula CPT is equal to del H del T at constant pressure. That means the enthalpy changes with the time. That gives us at constant pressure. That sorry, most yes, constant pressure, right? So cp value we can see that when cpt, that is the vary with temperature at different temperature, but for constant pressure we have the formula that is del H del T. And when we have the cv, that is constant volume at different temperature but at constant volume, that we have the del U del T. For Cp, we have some formula that is A plus Bt plus Ct square plus dt cube. These A, B, C, D, they are constant. In numerical, you can see the values of constant. And for Cv, for the determination, we have A plus Bt. Now we have all those formula. Then then enthalpy, this enthalpy, that means the H enthalpy changes, that means del H is equal to del U plus P del PV. That is our formula. Now if this del H is a function or the temperature, that when temperature changes are there, what happens in enthalpy changes? So there are several methods for calculating the enthalpy changes using this Cp value. Because Cp value, we have this formula that Cp value when changes with temperature, we have del H del T. Then for this type of program, we have the enthalpy changes, that is a formula that del H is equal to mCp dt. Okay, if this Cp is constant. Now another formula is there that del H is equal to m integration Cp dt when if when the Cp is changing with temperature. That time we need to use this formula. And heat capacity for most substances vary with temperature, where the values of Cp vary from the range. This ABCD. Actually, when Cp that changes with time, temperature, we have this formula how to calculate the Cp value. And that time, the pressure should be fixed and the all constant values will be given. Now one problem we can see and we can understand uh, all the theories, that the problem is what is the change in the enthalpy of 100 gram per second brine solution heated in a counter flow heat exchanger from 20 degrees centigrade to 80 degrees centigrade. Mass flow rate is given. Okay, then the temperature is given. If the not temperature changes, we can see if the average heat capacity at constant pressure is 3.12 kilojoule per kg Kelvin, then what is the changes of enthalpy? So that is written that average heat capacity is a constant. That means we need to apply this formula. So mass flow rate that is given, Cp value is given, T and T reference those are given 20 degree, 80 degree centigrade. Therefore, then we can calculate the value of del H. Now enthalpy changes is done, coming into the internal energy, that is del U. So change, what is change of internal energy? The change in internal energy, that is a function of heat capacity at constant volume. This is the formula. Since the heat capacity is a function of temperature and the mass, you should multiply mass by heat capacity as follows. Therefore, we have this formula that m integration T reference to T, CV dt. This is CV is the constant volume, T is the temperature, dt is the temperature changes, that's why the parameter, and M is the mass flow rate of the system. We have another numerical, that a closed rigid vessel that contains 200 kg of a fluid is heated from 20 degrees centigrade to 150 degrees centigrade. So T and T references both are given, and the mass, that is 200 kg, is given. Calculate the heat required for these purposes. Okay. So heat we need to calculate. The constant volume heat capacity of the fluid is given by the following relation. CV we need to calculate, and for CB we have one relation. And we have to calculate the internal energy part, that is a form of heat. Now for this CV calculation, A and V value, this is given, that A is 0.855 plus 9.42, that is a B, and temperature T is given. Now from this we need to calculate the value of CV, and when we have the CV value, we know the T and T references value, where T references is 20 and T is 150. So in this equation, we can put the value of T, that is the 150 degree centigrade, and mass flow rate 200 is given. So direct we can substitute the value into this equation. Then we have the value of Q, or you can say that is a del U. Q is written because internal energy form is a heat. Therefore, Q is written. Nothing else. Now, enthalpy. Uh, that we know the formula, that del H is equal to del U plus del PV. That is for a system. If this system is an ideal mixture, then the formula will change, and we have this formula, that H mix bar, that means the specific enthalpy at temperature, is equal to summation of all mixture. So xi, summation of xi hi bar. Okay. So for this ideal mixture, this assumption that a mixture behaves ideally nearly always works well for the mixture of gases, and it also works well for liquid mixture when the species being mixed are chemically similar. So this formula we can apply for gas as well as for liquid. So then what is the equation for non-ideal mixture? Am I audible? Hello?
Yes, ma'am.
Okay.
Yes, ma'am.
Actually, my cursor is rotating. That's why I'm thinking that maybe there is a network issue.
No, ma'am, you are audible.
Okay, okay. So if the system or mixture that is not ideal, for non-ideal mixture, we have this formula, that del H bar is equal to del U plus del UPV. This formula is for the non-ideal mixture. So there may also be change in volume when two species are mixed. In this case, the final volume of the mixture V does not equal the summation of the volume of the components that were mixed together. Now, same for the internal energy system. If it is a mixture, then the internal energy changes. The formula is U. That means this is a specific internal energy changes is equal to U mix That means only the specific internal energy of the mixture minus summation of the all mixture components. Okay, so that is written that ui is the specific internal energy for a pure species whose fraction, that is a mass or mole fraction depending on the units being used in the mixture of xi. So these internal energy changes, enthalpy changes for mixture, ideal and non-ideal. We just we have to just remember all these formulas. Okay. Now heat of the solution. Heat of solution, that means the temperature. So enthalpy of the mixture are often expressed in terms of heat of solution. Okay. তো এই হিট অফ সলিউশনে এটার জাস্ট টেম্পারেচারে কি করে চেঞ্জ হচ্ছে আমাদের মানে সেটা দেখলে আমরা বুঝতে পারবো মানে একটা একটা সিস্টেমের হিট কতটা প্রডিউস হচ্ছে, ঠিক আছে, সেটা মানে জাস্ট ইট ইজ এ চেঞ্জ ইন এনথালপি. Enthalpy means that the H value that result from dissolving 1 mole of solute in certain mole of solvent at a constant T. ঠিক আছে, just the enthalpy of a solution sometimes referred as a heat of solution, ঠিক আছে, or heat of dilution, you can say it is a heat of dilution. Now enthalpy calculation with phase change, এতক্ষণ যেগুলো পড়লাম সেগুলো enthalpy without phase change, এবার হবে with phase change. Phase change means that you are applying heat or you are working on the system. So what happens, the form will be changed. So what type of form we can see, like evaporation, then sublimation, then fusion. Okay, what is the vaporization? When the liquid parts that get evaporated, that is the evaporation. So that time the heat is required to changes the phase. That means when the liquid is transformed into vapor, so how much heat is required, that is expressed by the latent heat of vaporization. Fusion, when when a solid is melting and heat is required for this melting, the temperature, not temperature, the heat, this is known as a latent heat of fusion. Sublimation, that which is the heat required to directly vaporize a solid, that is known as a latent heat of sublimation. So latent heats means that is a function of pressure and temperature. Now we have a system that for a mixing. So the that is a mixing, মানে what happens if এতক্ষণ ধরে আমরা যেটা পড়লাম সেটা হচ্ছে যে কোনো একটা সিস্টেমের জন্য কি করে চেঞ্জেস গুলো হচ্ছে আমরা দেখলাম। মানে এনথালপি চেঞ্জ মানে ওটা সামেশন হয়ে যাবে ডেল ইউ প্লাস ডেল পিভি, ঠিক আছে। কিন্তু যদি কোনো মিক্সিং ইউনিটে হয় তার মানে ওখানে তোমার মানে মোর দ্যান 2 or 3 feedstock are there, you have to, and outputs are there, then you have to consider the all system, all feedstock and all outputs. So this is a mixing unit. We can see that stream 1, that is input, stream 2, that is a input, and m1 and m2, that is the mass, that are the mass flow rates of stream 1 and stream 2 respectively, and we have one output, that is m3. So for this system, what is the enthalpy changes formula? That is del H is equal to del H out minus del H, sorry, not a del, that is a summation. Summation H out minus summation H in. And this summation value or the enthalpy changes of a mixing is always zero. That is for an ideal mixing. এইখানে তোমরা দেখতে পাবে যাই হোক, এখানে একটা কথা লেখা আছে দেখো, ফর অ্যান আইডিয়াল মিক্সচার দ্য এনথালপি অফ মিক্সিং ইজ জিরো। এটা সবসময় মাথায় রাখবে, আইডিয়াল মিক্সচারের ক্ষেত্রে এনথালপি চেঞ্জেসটা সবসময় জিরো হয়। তো therefore here that is a mixture and we are assuming this is an ideal mixture, so del H, that is a differences between the summation of H out and minus summation of H in, and this is this differences is zero. Now if del H is zero, say, then what is del H? That is the output del H, that not del H, summation of H out. So we have one output, so this is H3, and summation of H in, we have two inputs, that is H1 and H2. Okay, so this gives us value. If you multiply this enthalpy with mass flow rate, then we have this equation. Now heat of formation. আচ্ছা, আমরা কিন্তু এখানে একটা হিট পড়েছি, দ্যাট ইজ হিট অফ সলিউশন। এটা কিন্তু আলাদা, ঠিক আছে? মানে হিট অফ সলিউশন মানে হচ্ছে তোমার একটা, তুমি যখন মানে একটা সলিউটকে তুমি যখন একটা সলভেন্টে মিক্স করছো একটা কনস্ট্যান্ট টেম্পারেচারে, তখন যে এনথালপি চেঞ্জেসটা হয় সেটা হচ্ছে হিট অফ সলিউশন, ঠিক আছে? তখন তোমার তো হিট প্রডিউস হতে থাকে, সেটা হচ্ছে ওই সলিউশনের হিট। কিন্তু এটা হচ্ছে হিট অফ ফরমেশন, that is different from the heat of solution. So what is heat formation? Heat formation, that we have formula, that del H bar degree Fi is equal to del H bar I minus integration of T references to T Cp T dt. This zero, that means all the system is in standard condition, and F, that is the for heat formation. Okay, and del H, that is the heat, we know that enthalpy of initial enthalpy changes, initial specific enthalpy changes, that is a experimental value. So that you can also you can say that that is a heat released or heat absorbed by the chemical reaction. This formula is applied when in a system we see the chemical reaction. Okay. Therefore, the heat, that time the heat can be released or heat can be absorbed. That means we sometimes we have endothermic reaction or the exothermic reaction. Okay. And CPDT, that is a specific heat capacity, and dt, and this formula when we need to apply when there is a no phase change. So to take account of possible energy changes caused by a reaction in the energy balance, you have to incorporate an additional quantity term as the standard heat of formation. ঠিক আছে, তার মানে হিট ফরমেশনটা কখন হচ্ছে? উইদাউট ফেজ চেঞ্জ, ইন প্রেজেন্স অফ কেমিক্যাল রিয়াকশন, ঠিক আছে? আর স্ট্যান্ডার্ড হিট অফ ফরমেশন, এটা হচ্ছে ডেফিনেশন, দ্য হিট অফ ফরমেশন ইজ জিরো ইন দ্য স্ট্যান্ডার্ড স্টেট for each element, কারের জন্য like carbon, oxygen, nitrogen, hydrogen, that at 25 degrees centigrade and 1 atm pressure, the heat of formation, that means the del H bar F, that is a 0. Okay? আচ্ছা, এবার হচ্ছে এনথালপি চেঞ্জেস, মানে তোমার এই যে ফর্মুলাটা বার করলাম, হিট ফরমেশন, heat of formation, if there is a phase change, then this formula only I have to incorporate this term, that del H bar TP. Okay, so and del H bar, that is a experimental value same, only this del HTP, this term, that is a sensible heat due to the phase change. Achha, what type of phase change we can see? That maybe the solid, that solid uh, that converted into liquid, then liquid change into the vapor, then from vapor you get again liquid, and from liquid you are getting the solid, or directly from solid you get the vapor. Okay, this type of phase change you can see. Now we have an example that solid changes to vapor. Now we have, first this is a phenol changes, so del H1, that is 25 degrees centigrade 1 atm, that is a standard process condition. So at this time this is a solid, so this is del H1 bar. Then you are increasing the temperature, but pressure is fixed. Okay, you are increasing the temperature, so after increment we have another heat of formation, del H2, then del H3, and that time you can see that is written SS. So in this both condition we have solid phase. Then when the temperature is 42.5 degree, suddenly the solid changes into the liquid, therefore L is written. You are increasing the temperature, so 181.4 degrees centigrade, at this temperature we have the liquid phenol. Okay, that time del H3 10%, the heat of formation. Again you are increasing the temperature, so 181.4 degrees centigrade 1 atm, again heat changes, maybe slight changes is there. So that time again we can see the del H changes, so del H4, therefore we, that time we have the liquid. But after increment, that when we have the 300 degrees centigrade, the liquid changes into the vapor phase, and that continue up to 3 atmospheric pressure, because when we have the vapor we cannot maintain the pressure, we cannot maintain the pressure, because vapor always gives us extra pressure, so that time the pressure is changing. So this way, for a phenol we can see that how the heat of formation or enthalpy changes are there. Mm. So for the total, so enthalpy changes, specific enthalpy changes for this total system, we have this formula, summation of all. Now we have two numericals here, that how to calculate this heat of formation from the chemical reaction. That the following enthalpy changes are observed experimentally for the reaction below 25 degrees centigrade in a standard state. Calculate the standard heat of formation of propylene. So first reaction, that propylene reacts with hydrogen, we have C3H8, then C3H8 that reacts with oxygen, we have the CO2 and H2O. Every time after the reaction we have this del H value. So when the del H value is negative, that means it is a exothermic reaction. That is a this means enthalpy changes, or you can say the heat formation. Okay, heat formation. So del H value, this negative means from this reaction we are getting heat. Then during second reaction again del H value that is negative. Third reaction del H value negative. Fourth reaction del H value negative. Now for four reaction we have different enthalpy changes or the heat of formation. So we need to calculate the standard heat of formation. Okay. Now mm, from this value, that means the del H value we have to calculate. Now how সাউন্ডটা কমা তো তিথি, সাউন্ড কমা. So first, if you consider equation number 1 and equation number 2, from this we can eliminate this C3H8 term. If one this equation 1 is subtracted from equation 2, or not yes, from balancing 1 and 2 we can eliminate this C3H8 term. Then we have this C3H6 plus H2 plus 5O2, and on the right side we have 3CO2 4H2O. Then del H value from this day, if you add these two equation, then from del H value we have this negative 560.2. One equation complete. Then for the third reaction and fourth reaction, these multiplying reactions 3 and 4 by 4 and 3, we need to multiply this equation number 3 by 4 and equation number 4 কেছে পরে দাঁড়াও by 3, and then we need to add. After that we have this equation. So after calculation we have two new equations. Now we have to subtract this equation from this equation. Then we have 3C plus 3H2 is equal to C2H6 and del H value. And now this del H value is giving positive value. So from this reaction we can say that now this del H is endothermic reaction. Now this formation of this is a actual formation of propylene reaction. So from this final calculation we can say the heat of formation is 4.85 kilo calorie. Okay. Hmm. Another example is there, that we have some chemical reactions, and from this reaction we have to calculate the heat of formation for zinc sulfate. Okay, same way you have to calculate. At first you have to just you have to just observe this equation, then you need to balance them. Suppose that first equation is Zn plus n is equal to Zns, and second equation you have 2 Zns plus 3 O2, that gives 2 Zno plus 2 SO2. Okay. Now first we need to eliminate this Zns part. Therefore we need to multiply this equation number 1 with 2. Okay, then you need to add. So after adding equation 1 and 2 you can eliminate the Zns. So finally you have 2 Zn plus 2s plus 3 O2. is equal to 2ZNO plus 2SO2. And same way, after adding this del H1 and del H2, you have 1 del H. Then you have to consider this equation number 3 and 4. So equation number 3 and 4, we have 2 SO3 in the right side and 1 SO3 in the left side of the equation 4. Therefore, we need to multiply this equation 4 with 2. Then we need to add. So I think on the next page you can see that 2SO2 plus O2 plus SO3, not SO3, plus Z 2ZNO is equal to ZnSO4. Yes, 2ZNO plus 2SO2 plus O2 is equal to 2ZnSO4. Now from this same way we get this del H. So then we have to know new equations, this one and this one. From this you have to again calculate, that means adding this 5 or 6 and finally cancelling the common terms. Then that means ZNO term will be cancelled, SO2 term will be cancelled, and you have the Zn2s, then oxygen, and in the right side you have ZnSO4. So for ZnSO4 you can calculate the del H value. This way you can calculate the heat of formation. আচ্ছা, আজকে এইটুকুই থাক, ঠিক আছে?
Okay, ma'am.
मैम अटेंडेंस की আপনি নেবেন?
হ্যাঁ হ্যাঁ হ্যাঁ, একটু নিচ্ছি।